Okay, guys, so we're going to talk about strategies for testing series. This is kind of like a review video now that you know all your testing, how you can determine if a series is convergent or divergent. And this will just be kind of a video on that. I was planning on making it a short video, but I'm not sure if that's going to be the case. I did about 7 examples below all of this that we'll go through together. So that might take at least 30 minutes. So here's kind of some rules for testing. Check and see if the test for divergence applies. Again, you always want to just look at the series and then the sequence that it's generated from. If you can tell just by looking at it that the limit of that sequence will not be 0, then you know it's divergent. Okay, so the divergence test is kind of your first thing you do just to double check. So maybe something really ugly and hard, you can just do the divergence test and you already win and say that it's divergent. Remember, the divergence test only applies for testing divergence. It cannot prove convergence. Then we have part 2, is the series obvious? So geometric, alternating, p-test, and telescoping, you guys all know those are very obvious series. You can tell just by looking at them. The telescoping normally has the denominator can be factored, usually into 2 binomials, and you go from there. Alternating series is probably the hardest of those 4. But a lot of alternating series problems, you could also maybe use ratio tests as well. But again, when you see something that you know is always, the sequence is always positive and it's always decreasing and it's continuous, then you normally say, hey, I might be able to do the alternating series test on this one. Okay, so is everything raised to the power of n? If everything's raised to the power of n, or you have an nth power, you can use the root test, obviously. Okay, so that one's pretty straightforward. And again, the root test is very obvious. Is there a factorial and or a product of exponential and polynomial functions? Okay, so if that's the case, if there's a factorial, normally factorial is a dead giveaway, and or a product of exponential and polynomial, we're going to use the ratio test. Okay. So we also have, is there a fraction with a lot going on? So meaning there's a whole bunch of stuff happening. You know, we're going to use the comparison test or the limit comparison test. Okay. And recall the LCT, okay, remember that the limit comparison test works, even when the direct comparison cannot be used. So remember, the direct comparison test sometimes fails, or the comparison test, that's, by the way, your book calls it the direct comparison test, and we just call it the comparison test, but that's the same thing. So whenever the inequality doesn't line up right, or you're not sure when it's greater than or when it's less than, and it's hard to figure out, that means that you could also still try the limit comparison test, and that might still work. So remember, the limit comparison test is kind of stronger than the comparison test. So just keep that in mind. Limit comparison test requires more work on your part, but it is a stronger test in my opinion. But the comparison test is very quick if you can get it to line up right. Is there an obvious U sub, or is the series easy to integrate? Well, then we know that will be the integral test. Okay, so remember, if you are asked to find the sum of a series, if they ask you, is it convergent or divergent, and then it follows with, if convergent, find the sum, then you know it has to be a geometric or a telescoping, right? The approximation thing we're kind of using right now for alternating series, but that's not the exact value, that's the approximation. So if they want to know the actual sum, then it's got to be a geometric or telescoping. So that should be a dead giveaway when you're dealing with one of those problems. Okay, so down here, I have a few problems that I wanted to practice with you guys. So let me zoom out a little bit. Okay, a lot of it, I guess. So for a minute, why don't you take a look at these and maybe pause the video and try to, before you just do them, why don't you try to write next to them what test you think you're going to use. Okay, so what test do you think will work with these particular problems? Okay. Okay, so now that you've unpaused the video, hopefully you've written next to each one of these what test would probably work. So now let's go and let's try a few of them. So determine if 1 plus n is convergent or divergent over n times 2 to the n. So I'm going to try the ratio test. This looks like a ratio test because it's got a polynomial times a factorial. So for me, this is going to be ratio test. And again, I love the ratio test because it feels so concrete. So the way the ratio test works is it says the limit as n approaches infinity of the absolute value of 1 plus n plus 1 all over n plus 1, 2 to the n plus 1 times the reciprocal of this, which would be n2 to the n over 1 plus n. Okay, so now let's see here. This would become limit as n approaches infinity, and the absolute values are unnecessary because everything, sorry about that, everything in there is positive, so we don't need the absolute values anymore. So this is going to be 2 plus n. Now let's see if we can get some canceling to go on here. So this 2 to the n will become 1, and then this 2 to the n will still be left with a 2 to the 1. And then this will become n plus 1 squared. So this is going to be 2 plus n times n all over 2 times n plus 1 squared, it looks like. Yeah. Okay, so now if we really want to write this out from here, we pretty much are done. Because I know this is going to be n squared, oops, limit as n approaches infinity of n squared plus 2n all over, and I think we can just leave it like this, n plus 1 squared. I think from here you guys know what's going to happen. So the numerator has an n squared, the denominator is also going to have an n squared, and then it'll be multiplied by 2. So the limit is going to end up becoming 1/2, which is less than 1, which means convergent by ratio test. Again, it's absolutely convergent, but in this case, it also implies convergence, okay? So be sure you write by ratio test, okay? Even if in the homework you're doing it or on the exam, it gives you a multiple choice for ratio test, you in your work still must write what test you're using, okay? So let's go over here to number 2, okay? So number 2 looks familiar. I feel like we did one of these in the comparison test. I don't know if it was in the homework. I think it might have been in the comparison test way back when we were integrating and using the comparison test with improper integrals. But this looks awfully familiar. So I'm going to say that this is comparison test. Okay. So what I'm going to do is I'm going to do my comparison as 2 over n squared. Okay, because I know that cosine of n at most could ever be 1. The biggest it could ever be is 1. Okay, so that means then that 1 plus cosine of n over n squared will always be less than or equal to 2 over n squared. Oops, let me put the series. So then this series, the sum of these two series must also be 2 over n squared must always be greater. But we know that this series right here, 2 over n squared, the series we're comparing to, is a convergent p series. So this is convergent by p series since 2 is greater than p equals 2 is greater than 1. Okay, so then we know because it's bigger and it's convergent, then that means that the smaller series must also converge. So by comparison test, 1 plus cosine of n over n squared must also converge. Okay. So that's pretty much all I would need to see for a problem like that, and we're done. All right. So now we come over here, and we have n cubed plus 1 and n to the fourth minus 1 as n equals 2 to infinity of this series. So the thing is when you run into something like this, you might want to be a little bit more careful. I feel like whenever you have a minus in the denominator, that means the denominator is actually getting larger. So if you were just going to take off the ones and had n cubed over n to the fourth, you would end up with 1 over n, but it's hard to say for sure. It's hard to say for sure which, let me see here. Let me just make sure. It's hard to say for sure which one is going to be bigger or smaller all the time. So what I would say is I'm going to try the limit comparison test. Whenever there's minus signs involved, I kind of get a little bit nervous about the problem and the direct comparison. So I kind of fall to the limit comparison, because then I don't have to worry about which one's bigger and which one's smaller. So I'm still going to use my comparison of 1 over n, because, my comparison series is going to be n cubed over n to the fourth. So that will be of 1 over n. So that's still going to be my series that I'm going to compare to. So what I'm going to do then is I am going to take, let's see here, a sub n. So we're going to take the limit as n approaches infinity of n cubed plus 1 over n to the fourth minus 1 times, well, it's actually divided by 1 over n, right? But dividing by 1 over n is actually the same as multiplying. So this is divided by 1 over n. So that's really the same as multiplying by n. Let's see here. So let's see what we get. So this would be the limit as n approaches infinity of n to the fourth plus n all over n to the fourth minus n. So once again, we know that this limit will equal 1, right? That's what we learned in L'Hopital's. But instead of doing L'Hopital's, we actually could just factor out. We also learned this in the chapter on horizontal asymptotes. As n approaches infinity, if the degree of the numerator is equal to the degree of the denominator, you can divide the leading coefficients. So we get 1. So this is 1, which is greater than 0, right? So this is greater than 0. So LCT applies, right? So that means since the series 1 over n is a divergent harmonic series, or the P series, you could also say divergent by p-test, then this series n cubed plus 1 over n to the fourth minus 1 must also diverge by LCT. And you're done. Okay, so that's how you can use the limit comparison test. And again, very little math, a lot of writing actually happening and explaining yourself, but very little math. Okay, let's go over here to number 4. What does that look like? Number 4 to me looks like an alternating series. Let's see if I have this one in my notes just to make sure. Yeah, I think this is an alternating series. Yep. Okay. So this is alternating series test. Okay. So, and you guys, by the way, you could write, if you wanted, instead of, to save time, you could just write alternating series test like that. Okay. So I'm going to use the alternating series test. And remember, the alternating series test, you have to show that it is, let me see, where did I lose it? You have to show that it is positive, and decreasing. Okay, so this is obviously a positive decreasing sequence. And you have to show that the limit is, what was I going to say? The limit is equal to 0. So we can show, now again, I'm just going to go back to our alternating series. So we have to show that this part of the sequence is decreasing. And we also have to show that the limit is equal to 0. Okay, so that's the two things that we have to do here. And we obviously know that it's also positive if you take off the -1. Okay, so I just want to go back to this. So n over n plus 2, n plus 3, so this is n plus 1 over n plus 2, n plus 3, is obviously smaller than n over n plus 1, n plus 2. Okay, so this is decreasing. Check. All right, so then we also need to, yeah, because the denominator is, you know, every term in the denominator is getting bigger, while the numerator is only getting slightly bigger, the denominator is getting much bigger. So this is definitely decreasing, okay? And then the limit as n approaches infinity of n over n plus 1, n plus 2 equals, oops. Well, I think you guys at this point, you can just say that this is 0. So that's check, because the denominator has an n squared term and the numerator has an n term. So then you know the limit's going to be 0 as n approaches infinity. So that's check. Okay, so that means that this is convergent by AST. And that is it. Okay, so this is convergent by alternating series test because the sequence, the limit of the sequence equals 0, and it is a decreasing sequence. Okay, so that's all you need to do for alternating series. That's pretty nice. Okay, now this one's slightly different. So we're going to use a little trick we learned, or a property of series. So we are allowed to split the series as long as both elements of the series are convergent. So we know that this is 1 over n cubed plus 1 over 3 to the n. Now, we know that this is a convergent p-series since p equals 3, and that's greater than 1. So convergent. And we know that this is a convergent geometric series since the absolute value of r, which is 1/3, is less than 1. Okay, so check. So the sum of two convergent series is also convergent. Check. So that's how you could do that one. Okay, so you're allowed to split it as long as both series themselves are convergent. Okay, so let's go over here to number 5. Oh, so this was a geometric and p series. Sorry about that. Forgot to write that on that one. Okay, so now let's go over to this one. Now this one looks an awful lot like a ratio test. So maybe the ratio test would work. But I feel like with just a little bit of manipulation, we can also use the root test, because you notice how everything's to the power of k, but like different variations of k. So what I'm going to do is I'm going to get rid of the variations. So this is actually 2 to the k, right? But then if you have 2 to the -1, wouldn't that just be 2 in the denominator? And then this would be times 3 to the k times 3, right? Because 3 to the k times 3 is the same as 3 to the k plus 1. And then this is times k to the k. So now I could rewrite this, and I could take the 3 and the 2 out. So this becomes 3/2 2 to the k times 3 to the k all over k to the k. Now that then becomes 2 times 3 over k all to the k. So then this becomes 3/2 k equals 1 to infinity. So now hopefully you guys see that this is 6 over k to the k. So now I can just say, well, the limit as k approaches infinity of the absolute value. Okay, so that could just be of the absolute value of the, oops, sorry. I think normally when we do the ratio or the root test. So if we go back here to the root test, oops, I want to just show you that the absolute value is inside the root. So we're going to take the limit of the absolute value of the root, what's inside of it, okay? So I'm going to take the limit of the kth root, and I'll just put the 3/2 in front, of the kth root of 6 over k to the k, and then the absolute values are unnecessary, but I'll write them. So this becomes 3/2 limit as k approaches infinity of 6 over k, right? Because these in a way cancel. And then this becomes 0, right? So because this is 0, this is less than 1. So we say convergent by root test. Okay, so the root test is kind of nice because we know that whenever the limit is less than 1, we get convergent by the root test. All right, so I think that's almost all of them. Let's do this one last one. Now here, this one has a factorial in it. So we're going to kind of lean on the ratio test, right? So let's try this. Let's say limit as n approaches infinity of the absolute value of n plus 1 factorial divided by e to the n plus 1 squared, right? Times e to the n squared all over n factorial, okay? But that is equal to, so as we go through this one, let me just make sure I have this one in my notes. I don't want to mess it up. Okay, let's see here. Oh, here it is. I have it in my notes right here. Okay, so let's see what happens. So let me write out a little bit. And again, the absolute values are unnecessary because everything's positive. So this just becomes n plus 1 times n minus 1, right? Dot, 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 e to the n squared. You know, I can cancel out some of these e's. You know what? I'm not even going to cancel it. I'm just going to write it. And then this will be e to the n squared times 2, oops, not times, plus 2n plus 1 times n minus 1, dot, dot, dot. Okay. So now let's see what cancels. So we know that this n times n minus 1 is going to cancel with that tail end of the factorial. We know that this e to the n squared is going to cancel with this. So what we're actually left with is n plus 1 all over e to the 2n plus 1. I feel like I'm missing something. Oh, okay, so we're here. Now the thing is this is basically infinity over infinity, right? So then we're going to do a little L'Hopital's. And this is going to become the limit as n approaches infinity of 1 over 2e to the 2n plus 1. But we know that that is 0, which is less than 1. So this is convergent by, and remember, I'm actually saying this series n equals 1 to infinity of n factorial over e to the n squared is convergent by ratio test. So hopefully that helps you guys. There could be like, I think on the exam, when I do an integral test problem, I'm going to say you must use the integral test for this problem, just because the integral test, I feel like, is a little bit overdoing it, and it's very time consuming, unless the integration is a very, very easy one. So again, with the integral test, I don't think I did one here, but the main time you use the integral test is if somebody tells you to, or if the problem looks like an integral you could just do off the top of your head, or a quick u sub or something. Other than that, you normally would probably want to check for something else. So actually, I only made the video 27 minutes, or a little bit less than 30 minutes, so that's good. But I just wanted to give you guys something to work on, to help you kind of strategize how to decide which series you're supposed to pick. All right, you guys, thanks for watching. See you in class.